So what are the 5 things? They are induction. Let's go with size. Electronegativity. T. Or we'll say charge too. Resonance. And of course, our favorite, hybridization states. So what's an example of induction? This versus this. So if I have 1 and 2, which one's more acidic? Which one has a more polar OH bond? Which one's a more Bronsted acidic? 1 or 2?
2.
2, absolutely. Why?
Because fluorine also pulls charges away from the carbon.
Yep, that fluorine is polarizing this bond. That's induction. Let's take a look at size. How does size play a role? HF versus HI. Which one's a more reactive acid? Notice I like to say reactive instead of weak or strong because I don't know it. Like, here's why it's confusing. A strong acid has what kind of bonds? Weak bonds. That's confusing. It's confusing to me, right? So I like to think about reactivity. Is a bond reactive or not? Reactive or unreactive? Which one's more reactive? HF or HI? HI. And that is because big old fat iodide, right? Less orbital overlap between that hydrogen and iodine because iodine's so much different in size. So it has reactive bonds. Another way of thinking about this, though, is let's think about I minus. I minus is huge. F minus is small. If you're large, you can, even not just resonance, you can spread out the negative charge. Right? If you're a big roly-poly iodide, you can be stabilized by spreading that charge out. Nobody? Everybody seeing this? My video cut out? Okay. Right? Big old fat iodide, right? I minus. So for a reaction to take place, there's 2 things that must be happening. Ready? Or one of 2 things. You either have reactive starting materials and or stable products. So in this case, what do we have? We have a reactive starting material, but then if we draw the conjugate base, we have a really stable conjugate base as well. So there's 2 ways you could look at this about why this reaction takes place. The reactivity of the starting materials or the stability of the products. Now we looked at hybridization later on, we'll get to that. That's a tricky one because it's not about the starting materials reactivity. It's more about the stability of the product that matters. Remember, it's an and/or statement. Also, the size is a periodic trend that goes up and down the columns. The one that goes from left to right, of course, is electronegativity. OH versus NH. Which one's more reactive? OH or NH? Which one's a more reactive acid? The OH, because oxygen is more electronegative. That's a more polar bond. Easy one. It's kind of like induction, too. You're thinking about that same one. And you could do the same argument as before. An O minus, all right, so I should draw these as real things. An O minus versus a, which one's more stable, O minus or N minus? Which one's happier with a negative charge? Well, O minus, it's more electronegative, right? So the star materials are reactive and the product is more stable. So resonance, which one of these is more reactive? Is it A or B? How is resonance playing a role? Resonance does what? Resonance makes things more stable, right? So you could draw a resonance structure, right? With this one, So what does that tell you about this hydrogen? It's a little more reactive, right? That resonance structure is telling me this is more reactive. Can this do resonance? No. So that's the starting material. What about the product? What about the conjugate base? Well, the conjugate base would look like this. Can that do resonance? Could this oxygen push electrons into the ring? Yeah. Is that going to make it more stable? Yeah. So things that can do resonance are more acidic. They're more reactive because they form stable products or they have more reactive starting materials. All right, so finally talking about hybridization state, we're looking at here is how does the difference in hybridization state affect acidity? And this one's interesting because it's really not about the reactivity of the starting materials as so much as about the reactivity or the stability of the products. So here's an atom that's sp hybridized. There's a carbon that's sp3 hybridized. So sp hybridized, sp3. And what we need to look at, you know this, that this is a pretty short bond. So this is not a very reactive or polar bond. Neither is this. This is actually a shorter bond. So this bond is actually a stronger bond than this one, but not by a lot. That matters, not by a lot. So what would the conjugate base look like for these two things? And that's what really matters, is we think about the conjugate base. So the two conjugate bases will look like this. Well, if that's the case, where is this lone pair located? What kind of hybrid orbital is it located? And what kind of hybrid orbital is that lone pair located in? Right? So this would be in an sp hybrid orbital, which, you know, is 50% s, 50% p. And this would be in an sp3 orbital, because sp3 hybridized, exaggerating here, which is a much longer orbital. Now the key here is, at the center part is the nucleus. And of course the nucleus contains protons, which are positively charged. And of course opposites attract. So if you're going to have a negative charge, you want to be as close to the nucleus as possible. An sp hybrid orbital is shorter and fatter than an sp3 hybrid orbital. Putting a lone pair in here would make it close to the nucleus, which makes it more stable. Putting a lone pair in here makes it farther away from the nucleus, which actually makes it more reactive. So here, in this case, why this is acidic is not because of reactive star materials. It's actually because you form a stable product. Versus this is very unstable because the electron density is in this sp3 orbital, which is really far away from the plus charge nucleus.